Good day, I'm Norman Wappinger. Today's video is a rather ambitious one. I want to set a direction for a large-scale view of modern geometry. So I want to give you an overview of how to think about geometry in a very general framework. So despite the rather light-hearted title, there's actually quite a serious intent in today's lecture. So when it comes to space, it's important to distinguish between our physical space, the one we live in, and the mathematical spaces that we want to create. Arguably, there's only one physical space, the one that we live in. For quite some time, for thousands of years, mathematicians assumed this is true of mathematical space too. This was sort of enshrined in Euclid's point of view, that the mathematical space was really just an idealization or reflection of the physical space. And so that one could argue and discover things by making constructions in physical space and then applying them to the mathematics. So until the 1930s, that is, when things started to change with the discovery of hyperbolic geometry, presenting really a new alternative to the question of what is space mathematically. But in retrospect, we can now see that, in fact, the idea of alternate geometries was around for a long time earlier, much before hyperbolic geometry. As spherical trigonometry had been an intense subject of investigation since Greek days. Not just the ancient Greeks, also the Hindus, the Arabs. In fact, many ancient civilizations were interested in spherical geometry because that was the geometry of the celestial sphere, the night sky. But also, before the 1830s, there was projective geometry that had been developed, and there was also, just a little bit before that, inversive geometry. So these were alternate ways of thinking about what geometry was, and so in retrospect, it shouldn't have been that much of a surprise that mathematically there are, in fact, a whole spectrum of different geometries. So in mathematics, in fact, there are lots of different kinds of geometries, just like there are lots of different kinds of pizza. And I'm going to use a pizza model for geometry because it's actually, I think, a quite instructive and relatively simple-minded way of organizing our thoughts about what are the building blocks or ingredients for the different kinds of geometries that are out there. So let me remind you, rather simplistically, that when you make a pizza, you have to make certain decisions. The first decision is probably what kind of base you're going to use. White flour usually, but perhaps you could use other kinds of flour to make the fundamental pizza dough. After you've chosen the base, you might decide on a type of pizza, whether you're going to have a thin crust pizza or a deep dish pizza. Okay, so there are basically these two different kinds of pizza that you could aim for. Then you should choose a size, whether you're going to make a small one, a medium one, or a large one. Or maybe if there's lots of people around, a family-sized pizza, or maybe even something much bigger. And then, perhaps the most interesting choice is what kind of toppings you're going to put on the pizza. Maybe pepperoni, or maybe mushrooms, or maybe onions, or maybe some combination of them. Or maybe if you're a purist, no toppings at all, just a base with a tomato sauce. Okay, after that, you slice the pizza up into pieces after you've made it, and then, of course, you consume it. So a very simple kind of model involving these sort of four types of decisions that you have to make. And we'll see that this is a good way of trying to remember how we can structure modern geometry. All right, so this basic orientation turns out to be useful for describing geometries in mathematics as well. So to define or to make a geometry, you choose, first of all, a base. But it's a base number system. Because these days, geometry is almost always built on top of arithmetic. So first of all, you have to choose a framework for arithmetic. For us, that's almost invariably the rational numbers. That, for us, is the fundamental arithmetical domain, with the operations of addition, multiplication, subtraction, and division, and nothing else. Just those four operations, that's arithmetic. But we've also seen occasionally that there are other alternatives. We might, for example, be interested in a finite field, or some other number system perhaps built up from the rational, maybe some kind of extension field. Or in fact, there's the possibility of using some quite different kinds of arithmetic. In any case, that's a starting point. That's sort of very analogous to choosing a base for making your pizza dough. Then you have to choose a type. And somewhat simplistically, but very good way of thinking, there's basically only two types: affine or projective. These two different ways of making a geometry, just like thin crust deep dish pizza. And then there's a size or dimension that you get to choose, whether you're working in 1 dimension, 2 dimensions, 3 dimensions, or maybe something higher, entirely analogous to the size of the pizza you're going to make. And then finally, additional structures. Once you have decided on these fundamental aspects of your geometry, you then get to decide what additional structures you're going to impose. These are like toppings for a pizza. Prominent amongst them are decisions about metrical structures. Okay, so there might be Euclidean metrical structure, or maybe relativistic metrical structure. There are other possibilities too. These are additional things that you impose upon this more fundamental base of your geometry that you've constructed from the first 3 choices. There's other things you can add too, so you can have distinguished points or distinguished lines. You might have some distinguished symmetries. So you might say this reflection is going to be given a name and will have a special role in the geometry. Or there might be a conic, or there might be a cubic, or there might be some additional collection of objects that you're going to specify as part of the definition of the geometry. There is a lot of variety possible here. Okay, so once we've made these different choices, well, then we have a geometry, and after that you subdivide it into pieces and eat it, or rather study it. All right, so let's have a look at these various ingredients separately. So the first one we've already talked quite a lot about, the need to establish a base number system. The definition of the kinds of numbers and the kinds of arithmetic that are going to be available to you to build up the objects of your geometry. And as I pointed out many times, for us, that's most of the time the rational numbers. That's sort of our default number system. So geometry in the modern approach is definitely built upon arithmetic, which is a reversal from millennia past. It's a very modern point of view. But in order to make this work, our arithmetic must be 100% solid. There's no room at all for compromise as to the integrity of the arithmetic if you're going to build geometry on it. So we must have completely well-defined notions of what the actual numbers are. Completely unambiguously defined. We must know very clearly what the arithmetical operations are. Make sure they're both explicit and well-defined, so they actually make sense. And we have laws of arithmetic with, hopefully, proofs associated to them. We have actually demonstrated the laws of arithmetic. And all of these ought to be underpinned by concrete, non-trivial examples. You've got to be able to actually demonstrate that you can do this arithmetic. It's not just an empty phraseology. It's not just something that happens over the hill. You're actually capable of taking out your pen, pencil, marker, and actually making computations. For example, over the rational numbers 2/3 plus 5/7. I know how to actually make this computation. It's not just empty words. I'm going to show it to you. 2 times 7 plus 3 times 5 over 21. That's the rule. So 2 times 7 is 14. 3 times 5 is 15. I have to add those. That's 29. Divided by 3 times 7, which is 21. And then I'm going to check to see whether there's any reduction possible. I don't have to do this, but it's nice. So 29 and 21 are relatively prime, so that's the final answer. I've demonstrated that I actually know how to do addition with rational numbers. And with multiplication, we can do that as well. 4 over 19 times 3 over 8, well, that's 12 over 19 times 8, whatever that is. But let's cancel the 4's. So we just have 3 over 19 times 2, which is 38. And that's the final answer. So we can demonstrate that we can do arithmetic. As opposed to the fairy tale world of real numbers that everyone pays lip service to, and very few can actually demonstrate that they actually can do the arithmetic. For example, pi plus e, supposedly, everything in quotes. Is anybody actually out there who will take up the challenge of telling us what precisely you get when you add pi plus e? I've asked you about pi plus e plus root 2 before. That's obviously too hard because nobody seems to be able to compute that for us. So let's simplify. How about just pi plus e? And after you've done that, why don't you demonstrate that you can multiply real numbers too if you're a fan? Tell us what pi times e is. And please, don't tell us that the answer is pi times e. And don't tell us that the answer here is pi plus e. Okay, that would be as facile as me saying that the answer here is 4 over 19 times 3 over 8. So real number arithmetic really doesn't cut it, as demonstrated by the lack of the ability of people to actually do real number arithmetic. It's not a philosophical issue. It's an issue of actually being able to do the arithmetic. So that's not what we want to use to build up geometry. The rational number arithmetic, there is something solid, dependable. We can all agree. We all know how to do that. That's the proper foundation. So now we have a good base. Now what do we do? So our next choices, we have to choose a type, which is affine or projective, and we have to choose a dimension. Choices are 1, 2, 3, or perhaps something higher. So it's very important understanding that there are really these two fundamentally different but related kinds or types of geometry. Affine and projective. Now, at various points in history, one or the other will be preferred. So in the 19th century, people were very enthusiastic about projective geometry. And there were many claims that projective geometry was really the fundamental geometry. In the 20th century, things changed a little bit, and affine geometry, or the associated vector space geometry of linear algebra, became dominant. But I think it's better that students of the subject have this balanced view towards things. There's an affine point of view, there's a projective point of view. They're both good points of view, they're both very powerful, and they complement each other in nice ways, and they interact naturally with each other as well. So we don't have to decide upon which one is best, but for any given geometry, we have to decide whether we're going to be talking about affine or projective geometry. All right, so let me illustrate the kinds of choices that we have here with this sort of schema here, where we start with low dimensions and work our way up a little bit. Okay, so in one dimension, we have affine one-dimensional space or projective one-dimensional space. And I remind you that an affine one point is just a rational number enclosed in square brackets, while a projective one point is a proportion enclosed in square brackets. And the affine one point has a interpretation as a point on a line like this, while the proportion has a interpretation of corresponding to a line in two-dimensional affine plane. Okay, so for example, this line here, which goes through the point 3, 1, which is actually a point in the affine two-dimensional plane, that determines this line, which we could say is the line 3 to 1. Okay, but there's additional structures really that are associated with these geometries. So when we're talking about the affine, say, one-dimensional situation, we're actually talking about some further assumptions as to how the coordinates are related to each other. And there's various ways of encoding that, but one way is through symmetries, about talking about what kinds of symmetries we're going to be interested in terms of preserving the structure of the underlying space. And the affine one-dimensional cases characterized by having these kinds of symmetries, where we're allowed to translate, and we're also allowed to scale. So if we scale everything by a factor of 3 and translate it over by 5, we think of that as being essentially the same geometry, a different kind of scale or a measurement, a setup, but essentially the same geometry. And in terms of measurement in this kind of context, well, we have this notion of relative signed lengths. The idea that this segment and this segment have a ratio of 1 to 2. Especially if we're talking about directed segment and a directed segment. Over here in the one-dimensional projective situation, the symmetries are a little bit more sophisticated. It turns out that they're given by linear transformations viewed projectively. So if we have numbers a, b, c, d, then we can consider this linear kind of transformation that takes a proportion x to y and sends it to the proportion ax plus by to cx plus dy. So we do require that this determinant be non-zero typically, and this is a kind of fundamental symmetry that we want to build in to our projective line. And there is a fundamental measurement here which is very, very important, okay, which we don't have a direct analog of here. It's called the cross ratio, and we're going to have to talk about that at some length. It's a very fundamental kind of building block for all of projective geometry. It already arises in this one-dimensional situation. All right, so one-dimensional affine, one-dimensional projective. This is sort of the simplest kinds of geometries that we can build up. Things get more complicated with each dimension that we go up. Okay, so two-dimensional affine and projective geometry. The affine plane or the projective plane. So here's a model of the affine plane. The basic objects are these affine 2 points, just pairs of numbers enclosed in square brackets. And we can visualize that by setting up a coordinate system, say x and y. And note that I've purposely not made them look perpendicular. So perpendicularity doesn't play a role for your basic affine geometry. That's only something that gets involved later on when we introduce some toppings. Okay. And I've also not made the measurement here look the same as the measurement in this direction. Along here we have an affine situation, so we are able to compare that this to this is in the ratio 1 to 1. And here similarly these are equally spaced. But there's no way of comparing the measurement in this direction with the measurement in this direction. And I illustrate that by visibly making them have different scales in different directions. All right, so here's the point 2, 1, which is 2 over this way and 1 over that way, and there's some parallelogram used to define that. So the notion of parallel lines here is a key part of the affine geometry at this stage. That is built into the affine geometry, though the perpendicularity is not. In terms of symmetries, well, symmetries are basically linear transformations in the sense of vector spaces and linear algebra, together with translations. So we're allowed to make a linear transformation which sort of amounts to changing the directions of these coordinate axes and changing the scale on the coordinate axes. And we're also allowed to take the whole picture and move it over, and that's substantially not any different. The geometry doesn't substantially change. In terms of measurements, well, in this two-dimensional setting we have the notion of relative signed areas. There's no notion of absolute areas here because the symmetries allow dilations. So there's no sort of unit area. We're only allowed to compare the areas of two oriented triangles. And relative signed lengths are available along any given line. So if you choose a line, there is a notion of relative signed length that this one is 3 times that one. Over in the projective setting, the projective plane consists of proportions x to y to z. in square brackets. And a way of visualizing that is to think in terms of lines in a three-dimensional space, represented by these axes x, y, and z. That's supposed to be three-dimensional space. And we're talking about lines through the origin in this three-dimensional space. That's our projective plane. And we're going to talk about symmetries, which are given by general linear transformations of x, y, and z, at least up to scaling, as long as the determinants are non-zero. And in terms of measurements, well, there might be some possibility of something that's some kind of generalization of the cross products that I mentioned in the first one-dimensional case. But the cross product is still a very important ingredient that occurs along any given line. And in these contexts, okay, we can define not just points and lines, but also it turns out we can talk about conics and cubics and triangles and polygons, and there's quite a lot of things that we can introduce to the geometry without any further additional structure, just at this point here. All right? So the basic affine plane, the basic projective plane, already very rich topics of geometry. But there's, at this point, no metrical structure in the sense of there's no units and there's no notion of perpendicularity yet. So this is not Euclidean geometry yet. Okay, it's sort of prior to Euclidean geometry. Even though, of course, historically, Euclidean geometry came long before these geometries were sort of envisioned. Okay, so, but nevertheless, sort of from a mathematical structural point of view, these are more fundamental and should be thought about as the pizzas, just the basic pizza made out of dough with a size and a type decided upon. So once we have these one-dimensional and two-dimensional geometries, we can look at analogs with higher dimensions as well. Three-dimensional affine, three-dimensional projective, and so on. And it turns out that then there's some kind of hierarchy, maybe starting with the affine one-dimensional, and then the projective one-dimensional, and then the affine two-dimensional, and the projective two-dimensional, and so on. In the sense that, in some sense, the affine one-dimensional space is sort of inside, or can be viewed as being inside, the one-dimensional projective space. And the one-dimensional projective space can be viewed as something sort of inside the two-dimensional affine space. In fact, we saw that in our pictures of it. So there's this sort of natural interleaving of these two geometries, one after the other. And so there's a kind of a connection. They're not really separate things. They're maybe aspects of some big total geometry that kind of includes all of them, perhaps. In addition, it's important to observe that the affine spaces, like AN, have associated to them vector spaces, which are sort of relative versions of the affine ones. Going back to the last talk, so instead of thinking about two absolute points in an affine space, we can also think about the relative position of those 2 points as represented by a vector. So we get something that looks a lot like the affine space and is actually probably a more familiar object from the point of view of modern linear algebra. So for example, the one-dimensional vector space might be represented by a vector with just one coordinate in round brackets, and the two-dimensional vector space would be a vector consisting of two rational numbers, also in round brackets, and so on. All right, so those are our base types of geometries. And now, to get more, to build something more interesting, we can, if we want, choose additional structure or structures. Now, it's important to realize that we don't have to. We can study the pure affine geometry, we can study the pure projective geometries, and they are very interesting and very fabulously rich subjects by themselves. But if we want to connect to our Euclidean world, then we have to impose something that makes things look more like our Euclidean world. In particular, that there's a notion of perpendicularity, and that there's a notion of measurement, being able to say that this segment and this segment are equal, whether it be length or quadrants or whatever we're measuring. All right, so this additional structure, which is often metrical structure, is imposed upon the underlying affine or projective spaces. And there's a variety of roughly equivalent ways of thinking about what a metrical structure is, or how to augment our base geometry with a metrical structure. So the terms that are used are a bilinear form, or a quadratic form, or an absolute conic, or in fact just a symmetric matrix. These are all roughly equivalent ways of introducing a metrical structure. And they can be added to either an affine or projective geometry. It's a very important point, which is perhaps not as well appreciated these days as it might be. So in algebraic geometry, there's a tendency to think about metrical structure as being mostly associated to affine geometry. But in fact, projective geometry is just as capable of supporting metrical structure as is affine geometry. It just becomes a little bit more complicated, but not less interesting. All right, when we do this, and we do it in a good way, we get notions of quadrants. We get notion of perpendicularity. And going up in dimension, we can measure higher dimensional things, quadria, some kind of analog of squared area, quadroon, some kind of squared volume, spread between two lines, which becomes very important, some kind of rational metrical equivalent or replacement of angle. And there are more things, okay? As you go up in dimension, there are more things that result from associating a quadratic form or symmetric matrix or bilinear form to an underlying geometry. This is rather abstract, so let's have a look at an example or two. So a very important example, the Euclidean plane, the familiar arena for doing Euclidean geometry. From this point of view, that's the affine plane together with an additional structure of a quadratic form given by, say, this matrix 1, 0, 0, 1. And that quadratic form manifests itself in the notion of quadrants of a vector. So it's often easier to describe this if we work in the associated vector space. So the quadrants of the vector xy can be expressed using a little bit of linear algebra and matrix multiplication in this form, or if you like, just directly as x squared plus y squared. So this notion of quadrants that we've talked about before can be naturally associated to this particular matrix. And that's a good way of thinking about things, because then you can say, well, what happens if we modify the matrix a little bit? Another way of thinking about that is to talk about the associated bilinear form, where you have one vector x1, y1, another vector x2, y2, and you take the dot product or inner product, which is x1, x2 plus y1, y2. So this is something that associates to a pair of vectors a number, rather than a number to a single vector. Another way of expressing the same content, essentially, is to specify the unit circle. If we know all the vectors whose quadrants is 1, then we essentially can figure out the quadrants of anything else in comparison. So the x squared plus y squared equals 1 unit circle. Once we have that, it gives us the notion of quadrants. And in fact, it also determines perpendicularity. It's another almost equivalent way of describing what this metrical structure is. It's allowing us to decide when two lines are perpendicular. In terms of the unit circle, perpendicularity can be thought of in terms of as the relationship between a radius and a tangent to the circle at that point. So that's one way of defining what perpendicularity is, that by definition the radius and a tangent are always perpendicular. In terms of vectors, this is an example of perpendicularity. 3, 4 is perpendicular to minus 4, 3, because if you take the dot product between them, you get minus 12 plus 12, which is 0. So dot product equals 0 is the algebraic manifestation of perpendicularity. So this is Euclidean geometry. It's what you get when you take A2, your base pizza, and you put on a single topping. The topping is basically this matrix, or one of the equivalent ways of manifesting the content of that matrix or associated quadratic form. bilinear form, circle, perpendicularity. So another interesting example is when we take that same two-dimensional affine plane and we impose on it a different metrical structure as a topping, where we impose a Lorentz or relativistic metrical structure. That's given by a matrix which is almost the same as the previous one, except it's 1, 0, 0, minus 1 with a minus sign there. The corresponding notion of quadrants is different because there's a minus sign there. It's x squared minus y squared. The associated dot product or inner product or bilinear form is different. It has the form x1, x2 minus y1, y2 between two vectors. The associated unit circle has a different form. It's going to be x squared minus y squared equals 1, which in our picture looks like this. It's quite different. The associated notion of perpendicularity is also different. So in this geometry, the vector 3, 2 is perpendicular to 2, 3 because the dot product is 3 times 2 minus 2 times 3, which is 0. Geometrically, it turns out that that's given by the same rule that we had in the Euclidean case. If you have a point on the unit circle, and you look at the tangent to the circle at that point, then that tangent is perpendicular to the radius. This is the center of the circle. That's a radius. And so that vector and that vector are perpendicular in this geometry. So historically, people would have said, but wait a minute, this is not the right geometry. It's not the geometry of our world. Okay, but it turns out to be rather subtle to decide what the geometry of our world is. Okay? We only see a relatively small part of the physical world. If we look at much bigger scales, if we look at much smaller scales, it becomes, first of all, hard to see clearly. And we start seeing strange things that we had no inkling of in our sort of scale. And as Einstein taught us, in fact, once we do look at a very large scale, then the geometry of the world becomes, in some sense, more like this kind of geometry rather than the Euclidean geometry of the previous example. At least when you include time as an extra aspect of the space story. So the question about what the true geometry of the physical world is still an open question. So we need to be flexible about mathematical geometries and not be too dogmatic that one is preferred over the other. Euclidean geometry has held sway for far too long, and it's only right and proper now that we have a more general approach and try to think a little bit more widely and broadly and flexibly about the different kinds of geometries and their various roles. Right, so this is a good starting point to think in terms of having a topping, something that you impose upon a base affine space in this case, to produce an interesting metrical structure, an interesting metrical geometry, which is different from the Euclidean one, but will share many features of it. All right, now let's have a final look at what you get when you take the projective plane and you add some metrical structure to it. There you get a whole different kind of variety of interesting geometries, notably including elliptic geometry and hyperbolic geometry. So these topics are really on the projective side of the story. Elliptic geometry is pretty close to being what's often called spherical geometry, basically the study of the sphere, the celestial sky, and astronomy, for example. And that's obtained by taking the projective plane and adding a projective quadratic form. In this case, the projective quadratic form that's determined by this matrix 3 by 3, which has ones down the diagonal. You need a 3 by 3 matrix. You might think you need a 2 by 2 matrix, but in fact a 3 by 3 matrix is the relevant thing. But it's a 3 by 3 matrix sort of up to multiples, so I have square brackets here. That means that if you multiply it by a scalar, it's not supposed to change. And that's because the projective plane itself consists of tuples x to y to z. There's really 3 components there. Okay, so when you when you do this, you get a geometry that's sort of geometry of the sphere, roughly, where a given line through the origin, which is basically your projective 2-point, intersects the sphere at least approximately in 2 antipodal points. All right, so elliptic geometry can be thought of as basically what you get when you take the projective plane and you add this particular quadratic form. While hyperbolic geometry is what you get when you take that same projective plane and you add a different projective quadratic form, one with a matrix 1, 1, minus 1 down the diagonal. Okay, in this case you get, instead of a sphere, you get a sphere that looks more like a hyperboloid of one sheet, and you're still looking at lines through the origin which meet this hyperboloid in 2 opposing points, at least some of the time. And you get what I call universal hyperbolic geometry, which is a very broad rethinking and extension of classical hyperbolic geometry and roughly far superior to it. Okay, so there's a lot more to be said here, and because this is a course in the foundations of mathematics, I don't want to say too much which is sort of waffly and imprecise, but this is an overview to give you an orientation. Okay, I don't expect you to know what elliptic geometry is precisely or hyperbolic geometry is precisely. I want you to have a rough orientation. Okay, we are going to be saying precisely what all these various things are because they're absolutely crucial sort of topics in modern geometry. Okay. But it's good to have an overall orientation. That is, that there are lots of different kinds of geometries out there mathematically. So when we talk about points and lines and measurements, we really have to do so in the context of a particular geometry. It's really necessary to start by saying, let's work in geometry X, where we remind ourselves that the main definitions are this, 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 and this. So we define the geometry, and then we can work inside it. Okay, so there might very well be all these different possibilities. In fact, there are these different possibilities around. So I hope this has given you an overall orientation. We are going to add detail to this picture, but this pizza model, I think, will hopefully stand you in good stead in terms of giving you a rough idea of the overall structure. In our next video, I want to take the transition. We've been talking a lot about affine geometry now. You can see that there's all these interesting things happening over on the projective side. So it's time that we moved over to the projective side, which is much less familiar to the modern student. Projective geometry used to be a major topic in mathematics in the 19th and in the early 20th centuries. But these days it's been very unfortunately on the decline. So we want to arrest that a little bit. And next time we're going to introduce really fundamental one-dimensional projective geometry. And I'll have the pleasure of telling you about one of the key formulas in this subject, which is actually one of the main formulas in all of geometry. It's the projective analog of the triple quad formula. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.